Pre-calculus lesson 2.5, zeros of polynomial functions. In this lesson, we're going to talk about how to find all zeros of polynomial functions and use those zeros to help us graph the actual polynomial. So far, we've talked about how we want to be able to find all zeros of a polynomial function, and sometimes we have to use synthetic division to do that. The rational zero theorem gives us a springboard on where to start to find one of those zeros. It says that if we have a polynomial in standard form that has integer coefficients and p over q, where p over q is reduced to lowest terms, is a rational zero of f, then p is a factor of the constant term a naught, and q is a factor of the leading coefficient. Another way of saying that is that all possible rational zeros of a polynomial must be a ratio of a factor of the constant term over a factor of the leading coefficient. So let's try this by listing all possible rational zeros of the function 4x to the fifth plus 12x to the fourth minus x minus 3. Notice here that we know that the constant term is negative 3 and the leading coefficient is 4. And so what we want to do here is we want to take the ratio of all possible factors of the leading coefficient, or sorry, of the constant term over the leading coefficient. Well, the factors of the constant term are going to be negative 3, positive 3, positive 1, and negative 1. Or we can also write that as plus or minus 3 and plus or minus 1. The factors of the leading coefficient, which is 4, are going to include plus or minus 4, plus or minus 1, and plus or minus 2. And so that means here then that all the list of possible rational zeros are going to be of the form of the factors of negative 3, or the constant term, over the factors of the leading coefficient, which in this case was 4. So that's going to lead us with plus or minus 3, plus or minus 1, over plus or minus 4, plus or minus 1, or plus or minus 2, which if we simplify and list these all out, will give us a list of plus or minus 1, plus or minus 3, plus or minus 3/4, plus or minus 3/2, and plus or minus 1/4, and finally plus or minus 1/2. This list right here would be where we know that our list of possible rational zeros must come from. In the next couple of examples, we're going to use the rational root theorem and also our leading coefficient test and our finding of zeros to help us actually graph the polynomial functions. So in part A, we're going to describe the behavior by using the leading coefficient test. Next, we'll find all possible zeros using the rational zero test. Then we will use that to factor or use synthetic division to find all the zeros. And then we'll give the behavior at the x-axis. Finally, we'll then factor the polynomial completely and use that information to sketch the graph of the function. Our first one here is going to be negative x cubed plus x squared plus 16x minus 16. Notice if we apply the leading coefficient test that we have a degree that is odd and a leading coefficient that is negative. So this right here, by using our leading coefficient test, will mean that we're going to have a rise to the right, or rise to the left, and a fall to the right. Next here, we want to be able to write out our factors of the constant term over the leading coefficient. Notice our constant term here is negative 16. And so all factors of negative 16 are going to be listed right there. Then we are also then going to find all factors of our leading coefficient, which in this case is just negative 1. So all possible rational zeros are going to be plus or minus 16, plus or minus 1, plus or minus 4, plus or minus 8, plus or minus 2. And so from here then, we're going to use synthetic division here to help us actually find synthetic division or factoring to help us find the possible zeros. In this case, since this is a 4-term polynomial, I'm going to go ahead and try to use grouping and see if we can factor. Just because if we were to use synthetic division, it'd be a lot of guess and check. So if we can factor, we want to go ahead and try that first. So if we group the first two together, we notice we can take out a negative x squared, because remember, we want that first term to be positive if possible. That will leave us with an x plus 1. And then the second two, we can pull out a 16, giving us an x plus 1. Giving us the two factors, negative x squared plus 16 times x plus 1. Again, in that first binomial, the negative x squared plus 16, I would like that to be a positive quadratic, so I'm going to go ahead and pull out a negative, leaving us with x squared minus 16. From here, we might note then that the x squared minus 16 is a difference of squares, that we can go ahead and split into x plus 4 and x minus 4. And so then we have our three factors here of x plus 4, x minus 4, and that x plus 1 with that negative sign on the outside, which is not going to affect our zeros. If we go ahead and set those all equal to 0, we will get the zeros of negative 4, a positive 4, and a negative 1. Notice if we go ahead and use these here, these three zeros all fall in the list of possible rational zeros that we found in part B. So that means that we're on the right track. Also in this case, since all of the zeros only appear once, that means they're all going to cross at the x-axis since they have an odd multiplicity. So if we go ahead and plot those 3 points, and then we include our end behavior, which we said was going to be a rise-fall, we're going to get a graph that looks like this. Please go ahead and pause here and check our answer using your graphing calculator or Desmos. Our next example is going to be the polynomial 6x cubed plus 25x squared minus 24x plus 5. If we look at this here, we notice that the leading coefficient is a positive 6 and the degree is 3. So using our leading coefficient test, this is going to be an odd degree with a positive leading coefficient, so this is going to be a fall to the left and a rise to the right. Next, we want to use our rational zeros test to find all possible rational zeros that we could use. In this case, our constant term is going to be 5, and so that all possible factors would be plus or minus 5, plus or minus 1, and the leading coefficient here is 6. So that includes plus or minus 6, 1, 2, and 3. And so if we list these all out, we have a possible zeros at plus or minus 5, plus or minus 1, plus or minus 5 6, plus or minus 5 halves, plus or minus 5 thirds, plus or minus 1 6, plus or minus 1 half, and plus or minus 1 third. So lots of different options here. But remember, this is giving us a shorter list than just guessing and checking all of these. If we look at this 4-term polynomial and we look at the first two terms, you might want to try grouping again. But if we look at the first two terms, we notice that there's really nothing that we can pull out that's going to help us. So in this case, what we're going to try to do is we're going to set this equal to 0. So if we set this equal to 0 and tried factoring, it would not come out nicely. So we're going to have to go ahead and try synthetic division using our list of possible zeros. So I'm just going to pick, in this case, try the factor x plus 1. So using synthetic division, if we use negative 1 and list our coefficients, remember, we will find that x plus 1 is a factor if we end up with a remainder of 0 using our remainder theorem. And so we're just going to have to go ahead and try synthetic division here. We're going to do that by bringing down the 6, and then we're going to keep on adding and multiplying until we find the remainder. In this case, our remainder here, though, is 49. So that means x plus 1 is not going to be a factor. So let's go ahead and try our next one. In this case, let's go ahead and try x minus 1. So that'll be a positive 1 as a 0. Let's go ahead and bring down the 6 and continue with our multiplication and adding. We're going to find that we get a remainder of 12. Still not 0. So x minus 1 is also not going to work. Notice how I'm picking the easier rational numbers for us to use with our synthetic division. Keep trying these first so it'd be easier to do the synthetic division until you actually find one that works. In this case, I'm going to go ahead and keep going and try x plus 5. So that means we're going to have a 0 of negative 5. If I go ahead and add and multiply once again, in this case, we find out, oh, hey, we did get a remainder of 0. And so that means that negative 5 is a 0 of the polynomial. And so from here, then, we can go ahead and use those leftover coefficients under our equation, our summation line, and that will give us our quadratic of 6x squared minus 5x plus 1. And this is a quadratic, which we know we can factor. And so our a times c is going to be 6, and our b here is negative 5. So we need two numbers that will multiply to 6 and add to a negative 5, which in this case would be a negative 3 and a negative 2. So if we go ahead and split up our quadratic and factor here, so we get that 6x squared minus 3x plus 2x plus 1, group the first two together, we can take out a 3x, which will leave us with a 2x minus 1. And the second two, we can only pull out a 1, which will leave us with a 2x plus, that should be a minus there, my bad. So it'd be a negative 1, which will leave us with a 2x minus 1. So our two factors are 3x minus 1 and 2x minus 1. And so we can go ahead and set those equal to 0, and that will give us the rational zeros of 1/2 and 1/3. So we have found that our three zeros are -5, 1/3, and 1/2, which were all listed in our list of possible rational zeros, which is a good thing. Using those zeros then, we can use that to help us graph. And so if we go ahead and plot these here, in this case, since they all only appear once, that means they have odd multiplicity. So at each of our zeros, they're only going to cross the x-axis. And so if we go ahead and plot those, there's our -5, 1/3, and 1/2. And using our end behavior, which we said was going to be a fall rise, we're getting this kind of weird S-curve shape to this graph. Please pause here and use Desmos or your graphing calculator to check our work.